The question that I have is, could you do an example on the use of the graphical method of solving 2D seepage problems? Here is the example. This dimension here is 10 meters and this dimension here is 6 meters. So basically we are looking at a seepage tank problem. The head difference, the capital delta H, is 4 meters. So let me go ahead and list them here. So delta H is 4 meters. And ends of F, which is the number of flow channels, we have 3 of them here. And ends of E, which is the number of equipotential drops, we have 6 of them in this flow net. Let me give you a value for the permeability. Let's just say permeability equals 0.1 meter per second. So now we take these numbers and substitute in this equation to calculate the volume rate of water flow. So permeability is 0.1 meter per second. I'm going to keep the units in there, and then capital delta H is 4 meters. NF is 3 meters, 3, and NE is 6. Let's just say we consider 1 meter into the paper. Alright, so we have to multiply this by the width of the seepage tank. So now you simplify all of these, and I get 0.2 meter cubed per second for the volume flow rate. Let's talk about a few other things. I want to calculate the pour water pressure at point K. The procedure is exactly the same as the one that we already talked about for one-dimensional problems. You calculate the total head at point K and you figure out the elevation head. Obviously that should be given to you. And then you can calculate the pressure head simply by subtracting the elevation head from the total head. Then the pour pressure is pressure head multiplied by the density of water. Point K is roughly halfway between this equipotential line and this equipotential line, and therefore the total head at point K can be approximated as H1 minus maybe 4.5 times delta H. There are 6 equipotential drops, and therefore little delta H equals big delta H divided by 6. I put some numbers here so we can do this numerically. So using these numbers, I get a total head of 7 meters at point K. This distance is given as 2.5 meters, and therefore the elevation head is 2.5 meters. This leads to a value of 44.1 kilopascal for the pour water pressure at point K. So this is the general procedure for calculating the pour water pressure whenever there is water flow in soil. Supposing, say, we are getting ready to design the sheet pile wall and we want to evaluate its stability by considering all of the forces that are acting on it. And we have water pressure on the left side, we have water pressure on the right side, we have soil pressure on the left side, we have soil pressure on the right side. So let's consider the water pressure, all right? So from here to here, we have hydrostatic water pressure. So that's pretty easy to calculate, right? And then if I were to calculate the pour pressure at this point, and I need to follow this procedure for calculating the pour pressure at that point because there is water flow taking place now. And similarly, I calculate the pour pressure at point C by following this procedure. So now I have the pour water pressure at discrete points inside the soil with water flow. So now I have a complete distribution of the pour pressure acting on the left side of the sheet pile wall. I follow the same procedure to calculate the pour pressure on the right side. So now I have a complete description of the pour pressure distribution on the sheet pile wall. And then you take it from there and add the pressure coming from the soil, which we will consider in another chapter later on. And you use a similar procedure for calculating the uplift pressure at the bottom of a concrete dam, and we'll do an example on that a little later. Now let's say I want to check and see if there's a potential for piping failure. If piping is going to happen, it's going to happen in this region. This is the most critical region in the whole of soil domain. This is where the water is flowing upward. If I can approximate this region by a rectangular pipe, then this problem is approximately the same as the one-dimensional problem we considered earlier. This EDLM is comparable to the soil column in this 1D setup. So if I can measure this vertical distance little l, then I can calculate the hydraulic gradient by this equation, little delta H divided by L. We compare this hydraulic gradient, the actual hydraulic gradient, with the critical hydraulic gradient, which if you recall is given by this equation for this setup right there. And then usually we define a factor of safety against piping by this ratio here, I critical divided by I. So you want this ratio to be as high as possible, obviously, so definitely greater than 1, and maybe 1.5, 2, something like that. So here I picked some numbers just to illustrate how we do these calculations. So I assumed L is 0.8 meter, then the hydraulic gradient works out to be 0.834. And let's just assume that gamma sat is 18 kilonewton per meter cubed, then gamma prime is 18 minus 9.81, which is 8.2 kilonewton per meter cubed. Then the critical hydraulic gradient is calculated to be 0.84, and your factor of safety works out to be 1.007, which of course is not high enough to assure safety against piping. Before I leave this slide, I want to make two notes here. Number one, when you don't have enough information to calculate gamma set, I critical equals 1 is a good starting value. That is because usually gamma set is twice as much as gamma W, and therefore I critical is roughly equal to 1. Second note that I want to make here is that this formula here, if you recall, is valid only for homogeneous soil. So if you do have a complicated layering in this toe region, then this equation is not valid. So you have to kind of go back and calculate this based on the fundamental. The fundamental is piping occurs whenever the effective stress is 0, right? So you calculate the effective stress at a certain point and set that to 0, and that becomes your condition. That is the basis for your calculations.